moving along. So now we're going to kind of get into this weird land. You notice here now, all of a sudden I jump randomly to chapter 15.4 and 15.5. And I have these crazy things on here. I'm only going to talk about this very briefly. And in the learning goals, I only want you to be familiar with the following, not to like full, PhD thesis. But if you do want to read in more depth, I would suggest chapter section 15.4 and 15.5. And we've already looked at a little bit of 15 when we talked about partition functions. And hopefully you see that right there. That's somewhat familiar. But now I want to connect this idea that we talked about, partition functions, states, and entropy. Okay? And so we start by defining an ensemble. Okay? And an ensemble, I'm going to turn to a page in my book here just so I can read the correct definition, so I make sure I get it correct too. So an ensemble is a collection, and it can be dependent. It's a collection of states, okay? And that collection of states is dependent on what is being held constant, okay? So we have three different types of ensembles. There's the canonical, there's the microcanonical, and then there's the grandcanonical. Everything that we will do in this class is related to the canonical ensemble, okay? So what is the canonical ensemble? So we start by saying we have some closed system. So that means and this is just with respect to the canonical, okay? Don't mix this up with microcanonical and grandcanonical, okay? As it turns out, microcanonical is also closed, and I'll show you how we can tell in a moment, all right? So we start off with the closed system. I'll talk about this I in a moment. And in this closed system, we use the number of particles, or I'll just say number of things, that could be molecules, atoms, right? Electrons, whatever we want. It's the number of things, okay? And of course, we have V for, I ran out of room here, volume. And of course, T for temperature, okay? So this is what makes this a closed system, is that we are fixing the number of things in this box, okay? And so you notice here on the microcanonical, also closed system because the number of things in that box are fixed. But in the grandcanonical, this is an open system, free to exchange heat and mass, okay? So in the canonical system, it's a closed system with fixed composition, and we describe that system by use of the microstate, okay? So in other words, the sum total of N, V, and T gives us the macro state, okay? So the number of things, or the volume, or the temperature, that is what we refer to as the state. We've called this state function before, right? And I can call a state function P as a function of N, V, and T, right? And that will describe the macro state. Well, in this canonical ensemble, we say there is I number of these states, which we call microstates, and each one of those represents an equivalent way we can arrange this system and have the same energy, okay? So I'll say that again. The microstate represents the number of unique ways we can arrange, in case of the canonical, the ways that we can arrange the number of particles, the volume, or the temperature, the number of ways we can do that and still result in the same energy, okay? And as it turns out, that can be calculated with a partition function, and specifically we call this the canonical partition function, and it's the same partition function we've been looking at. So when we derived the Maxwell-Boltzmann distribution, that was derived from the canonical partition function, okay, which says the sum of all of these microstates is e to the negative beta times the total energy, or the energy of that state, I, where remember beta is 1 over k Boltzmann T. So we've already seen this partition function that we've already been looking at is what we call our canonical partition function, and it's specifically with respect to the macrostates composition, volume, and temperature. Okay, I'll get into a little bit more detail on these microstates momentarily and what this all means. So now you can see with the microcanonical ensemble, it's the number of ways in which we can arrange number of particles, volume, but now instead of temperature, energy. Okay, and in the grand canonical, it's a wide open system, so there's no fixed number of particles. However, volume and temperature are fixed in the grand canonical, as well as this term mu that we call chemical potential. And I'm going to describe that as we'll talk more about chemical potential as we move forward. Okay, so that's all I really want to say about ensembles. For those of you that go on to graduate school and do, PChem, like you will take a statistical mechanics class and a statistical thermodynamics class. You will go into huge, hideous, disgusting detail on these partition functions and these various ensembles. I only just wanted to touch on this briefly and just make you somewhat familiar of what an ensemble is and how that leads to microstates.